In this video, we're going to be reviewing the binomial distribution. So the binomial distribution is a discrete distribution. That means it takes only values that are positive integers, 1, 0, 1, 2, 3, 4, etc. It has two parameters, n the number of trials and p the probability of success. And the conditions for the binomial distribution are there has to be a fixed number of trials, two possible outcomes, generally called success and failure, constant probability of success, and each trial is independent of all others. So what you get one go doesn't impact the second go or the third go, and so on. And if x is defined as a random variable following a binomial distribution, we write x is distributed with that little squiggle, binomial for b, n and p are the two parameters. So this is a typical past paper question. There's often lots of different parts to it, so this is quite a big one, and we have to do everything in this question. So we're going to split it up a little bit and look at the first part first. So here we're just going to use a straightforward binomial. On average, 10% of the tiles are faulty, so we know the probability of failure, and there's a sample of 18 tiles. So we first of all define our random variable x. We can say that's faulty tiles. So x is distributed binomially, 18 for the number of tiles and 0.1 for the probability of being faulty. So find the probability that there are exactly two faulty tiles in the sample. Well, all we're going to do is use the calculator. We've got to use our calculator properly. So when we do this, we're going to go to the binomial, the PD function, which gives us an individual value. Okay, as we've done before, we know that x is 2, that's the two tiles, n is the number of tiles out there. So that was our 18, and p was 0.1, the probability of success. And then we're just simply going to press equals, and there's our probability of that x equals 2, so 0.28351. And we're going to give our answer to a sensible degree of accuracy, 3 or 4 significant figures. It would be suitable, so I can give it to 3 significant figures here. Now, for x is more than 2 faulty tiles, that means x is greater than 2. Now we have to understand here, this is a discrete distribution. So to do this, we need to think about how else can we write it, because our calculator will only give us the value less than or equal to a number. So if you look how I've split it up here, I've got circled greater than 2, and in the rectangle 0, 1 and 2 is less than or equal to 2, which is what the calculator would give you. So the probability that x is greater than 2 is 1 minus the probability that x is less than or equal to 2. So to work out our required probability, we've got to find that x is less than or equal to 2. This time we're going to use the other function for the binomial. So we go into it exactly the same way, but instead of using the PD function, we're going to use the CD, the cumulative density function. Okay, and I'm going to go for the variable. X is less than or equal to 2 is already written on there, and the parameters are actually the same as they were before. So that is 0.33795. Okay, so I've given that to 4 significant figures. I'm now going to work out my answer, and then writing that to 3 significant figures, 0.266. What I'm not doing is just writing to 1 significant figure or anything like that. And to find the expected number of faulty tiles, well, the expectation is just n times p, so we expect to have 1.8 faulty tiles. Okay, so now we're doing a hypothesis test. So our two hypotheses, the first one, h0, p is equal to 0.1, nothing's changed. But we're expecting there to be more faulty tiles, so we're saying p is greater than 0.1. Now, if we're doing this, we need to define what p is going to be. We should always do this. This is worth a mark. So where p is the population proportion of faulty tiles. Now, why are we using p is greater than 0.1? Well, that's because we're expecting there to be more faulty tiles than there were previously. Now, the critical region, this is where we will reject the null hypothesis. So this is the value where we're going to reject it. So to do this, we have to test different values of n to satisfy the condition that x is greater than or equal to n is less than 0.05 or 5%. So the first thing we're going to do is define our distribution. So under H0, x is distributed binomially 18 and 0.1. 0.1 because we're saying everything's the same. So we're going to find x is greater than or equal to 3. I've arbitrarily started somewhere. Well, I know this is the same as 1 minus the probability that x is less than or equal to 2. I can use that on my calculator because that gives me the value straight away. And in fact, we've actually done this one before. So if you remember, x was 2, this is the cumulative density one, n is 18, and p is 0.1. So we can just go through and press our equals button, and we've already had this result in the previous part of the question, 0.7337. Okay, so I can work out the value of that. If that value is less than 0.05, then I'm happy and I'm winning. But this one isn't, 26.6%. So we still accept H0. So we try x is greater than or equal to 4. Well, that's the same as 1 minus the probability x is less than or equal to 3. Again, I can use my calculator to determine that value just by changing the 2 into a 3. All the other parameters will remain the same. I get my value 0.9018. So work out 1 minus 0.9018. And that's going to give me a value of 9.82%. Well, again, it's not in less than 5%, so I still accept H0. So I try another one. X is greater than or equal to 5. Well, that's 1 minus probability x is less than or equal to 4. So changing my 3 into a 4 on my calculator again. And I get a probability of 0.9718. So 1 minus that probability, and it gives me an answer of 0.0282. So that is less than 5%, so I reject H0. I have found my critical region. My critical region is anything where x is greater than or equal to 5. Now the question asked me, when x equals 4, what would I do? Well, that was the test statistic. That was how many tiles have been broken. So I would accept H0. There is insufficient evidence to say that the proportion of tiles that are broken has increased.